React, Synergizing Reasoning and Acting in Language Models by Shunyu Yao, Jeffrey Zhao, Dian Yu, Nan Du, Ishak Shafran, Karthik Narasimhan, Yuan Cao. Abstract. While large language models, LLMs, have demonstrated impressive performance across tasks in language understanding and interactive decision-making, their abilities for reasoning, e.g. chain of thought prompting, and acting, e.g. action plan generation, have primarily been studied as separate topics. In this paper, we explore the use of LLMs to generate both reasoning traces and task-specific actions in an interleaved manner, allowing for greater synergy between the two. Reasoning traces help the model induce, track, and update action plans, as well as handle exceptions, while actions allow it to interface with and gather additional information from external sources, such as knowledge bases or environments. We apply our approach, named REACT, to a diverse set of language and decision-making tasks and demonstrate its effectiveness over state-of-the-art baselines in addition to improved human interpretability and trustworthiness. Concretely, on question answering, hotpot QA, and fact verification (fever), REACT overcomes prevalent issues of hallucination and error propagation in chain-of-thought reasoning by interacting with a simple Wikipedia API and generating human-like task-solving trajectories that are more interpretable than baselines without reasoning traces. Furthermore, on two interactive decision-making benchmarks, ElfWorld and Webshop, REACT outperforms imitation and reinforcement learning methods by an absolute success rate of 34% and 10% respectively, while being prompted with only one or two in-context examples. One introduction. A unique feature of human intelligence is the ability to seamlessly combine task-oriented actions with verbal reasoning, which has been theorized to play an important role in human cognition for enabling self-regulation or strategization and maintaining a working memory. Consider the example of cooking up a dish in the kitchen. Between any two specific actions, we may reason in language in order to track progress. Now that everything is cut, I should heat up the pot of water to handle exceptions or adjust the plan according to the situation. I don't have salt, so let me use soy sauce and pepper instead. And to realize when external information is needed, how do I prepare dough? Let me search on the internet. We may also act, open a cookbook to read the recipe, open the fridge, check ingredients, to support the reasoning and to answer questions. What dish can I make right now? This tight synergy between acting and reasoning allows humans to learn new tasks quickly and perform robust decision-making or reasoning, even under previously unseen circumstances or facing information uncertainties. Recent results have hinted at the possibility of combining verbal reasoning with interactive decision-making in autonomous systems. On one hand, properly prompted large language models, LLMs, have demonstrated emergent capabilities to carry out several steps of reasoning traces to derive answers from questions in arithmetic, common sense, and symbolic reasoning tasks. However, this chain-of-thought reasoning is a static black box in that the model uses its own internal representations to generate thoughts and is not grounded in the external world, which limits its ability to reason reactively or update its knowledge. Figure 1. Comparison of four prompting methods: A. Standard, B. Chain of thought, COT, reason only, C. Act only, and D. React, reasons act, solving a hotpot QA question. 2. Comparison of A. Act only and B. React prompting to solve an ElfWorld game. In both domains, we omit in-context examples in the prompt and only show task-solving trajectories generated by the model, act, thought, and the environment, OBS. This can lead to issues like fact hallucination and error propagation over the reasoning process, Figure 1.1b. On the other hand, recent work has explored the use of pre-trained language models for planning and acting in interactive environments, with a focus on predicting actions via language priors. These approaches usually convert multimodal observations into text, use a language model to generate domain-specific actions or plans, and then use a controller to choose or execute them. However, they do not employ language models to reason abstractly about high-level goals or maintain a working memory to support acting, barring Huang et al. 2022b, who perform a limited form of verbal reasoning to reiterate spatial facts about the current state. Beyond such simple embodied tasks to interact with a few blocks, There have not been studies on how reasoning and acting can be combined in a synergistic manner for general task solving, and if such a combination can bring systematic benefits compared to reasoning or acting alone. In this work, we present REACT, a general paradigm to combine reasoning and acting with language models for solving diverse language reasoning and decision-making tasks. Figure 1. REACT prompts LLMs to generate both verbal reasoning traces and actions pertaining to a task in an interleaved manner, which allows the model to perform dynamic reasoning to create, maintain, and adjust high-level plans for acting, reason to act, while also interact with the external environments, e.g. Wikipedia, to incorporate additional information into reasoning, act to reason. We conduct empirical evaluations of REACT and state-of-the-art baselines on 4 diverse benchmarks: question answering, fact verification, text-based game, and web page navigation. For Hotpot QA and Fever, with access to a Wikipedia API that the model can interact with, REACT outperforms vanilla action generation models while being competitive with chain-of-thought reasoning. The best approach overall is a combination of REACT and chain of thought that allows for the use of both internal knowledge and externally obtained information during reasoning. On ElfWorld and Webshop, 2 or even one-shot REACT prompting is able to outperform imitation or reinforcement learning methods trained with 103 to 105 task instances, with an absolute improvement of 34% and 10% in success rates, respectively. We also demonstrate the importance of sparse, versatile reasoning in decision-making by showing consistent advantages over controlled baselines with actions only. Besides general applicability and performance boost, the combination of reasoning and acting also contributes to model interpretability, trustworthiness, and diagnosability across all domains, as humans can readily distinguish information from models' internal knowledge versus external environments, as well as inspect reasoning traces to understand the decision basis of model actions. To summarize, our key contributions are the following. 1. We introduce REACT, a novel prompt-based paradigm to synergize reasoning and acting in language models for general task solving. 2. We perform extensive experiments across diverse benchmarks to showcase the advantage of REACT in a few-shot learning setup over prior approaches that perform either reasoning or action generation in isolation. 3. We present systematic ablations and analysis to understand the importance of acting in reasoning tasks and reasoning in interactive tasks. 4. We analyze the limitations of REACT under the prompting setup, i.e., limited support of reasoning and acting behaviors, and perform initial fine-tuning experiments showing the potential of REACT to improve with additional training data. Scaling up REACT to train and operate on more tasks and combining it with complementary paradigms like reinforcement learning could further unlock the potential of large language models. Synergizing reasoning plus acting. Consider a general setup of an agent interacting with an environment for task solving. At time step T, an agent receives an observation ot in O from the environment and takes an action at in A, following some policy pi 8 CT, where CT equals O1A1, OT-1 H1 is the context to the agent. Learning a policy is challenging when the mapping CT7 at is highly implicit and requires extensive computation. For example, the agent shown in Figure 1.1c is unable to generate the correct final action, Act 4, to finish the QA task as it requires complex reasoning over the trajectory context. Question, Act 1.3, OBS 1.3. Similarly, the agent shown in Figure 1.2a fails to comprehend from the context that Sink Basin 1 does not contain Peppershaker 1, thus keep producing hallucinating actions. The idea of REACT is simple. We augment the agent's action space to A equals AL, where L is the space of language. An action at in L in the language space, which we will refer to as a thought or a reasoning trace, does not affect the external environment, thus leading to no observation feedback. Instead, a thought at aims to compose useful information by reasoning over the current context CT and update the context CT plus 1 equals CT at to support future reasoning or acting. As shown in Figure 1, there could be various types of useful thoughts, e.g. decomposing task goals and create action plans, 2B, Act 1, 1D, Thought 1, injecting common sense knowledge relevant to task solving, 2B, Act 1, extracting important parts from observations, 1D, Thought 2-4, track progress and transit action plans, 2B, Act 8, handle exceptions, and adjust action plans, 1D, Thought 3, and so on. However, as the language space L is unlimited, learning in this augmented action space is difficult and requires strong language priors. In this paper, we mainly focus on the setup where a frozen large language model, Palm 540b1, is prompted with few-shot in-context examples to generate both domain-specific actions and free-form language thoughts for task solving. Figure 1, 1D, 2B. Each in-context example is a human trajectory of actions, thoughts, and environment observations to solve a task instance, see Appendix C. For the tasks where reasoning is of primary importance, Figure 1.1, we alternate the generation of thoughts and actions so that the task-solving trajectory consists of multiple thought-action-observation steps. In contrast, for decision-making tasks that potentially involve a large number of actions, Figure 1.2, thoughts only need to one, we show some GPT-3 results in Appendix A.1 which outperforms Palm 540b, appear sparsely in the most relevant positions of a trajectory, so we let the language model decide the asynchronous occurrence of thoughts and actions for itself. Since decision-making and reasoning capabilities are integrated into a large language model, React enjoys several unique features. A. Intuitive and easy to design. Designing React prompts is straightforward, as human annotators just type down their thoughts in language on top of their actions taken. No ad hoc format choice, thought design, or example selection is used in this paper. We detail prompt design for each task in sections 3 and 4. B. General and flexible. Due to the flexible thought space and thought action occurrence format, React works for diverse tasks with distinct action spaces and reasoning needs, including but not limited to QA, fact verification, text game, and web navigation. C. Performant and robust. React shows strong generalization to new task instances while learning solely from 1 to 6 in-context examples, consistently outperforming baselines with only reasoning or acting across different domains. We also show in Section 3 additional benefits when fine-tuning is enabled, and in Section 4 how React performance is robust to prompt selections. D. Human-aligned and controllable. React promises an interpretable sequential decision-making and reasoning process where humans can easily inspect reasoning and factual correctness. Moreover, humans can also control or correct the agent behavior on the go by thought editing, as shown in Figure 5 in Section 4. 3. Knowledge-intensive reasoning tasks. We begin with knowledge-intensive reasoning tasks like multi-hop question answering and fact verification. As shown in Figure 1.1d, by interacting with a Wikipedia API, React is able to retrieve information to support reasoning, while also use reasoning to target what to retrieve next, demonstrating a synergy of reasoning and acting. 3.1 Setup domains. We consider 2 datasets challenging knowledge retrieval and reasoning. 1. Hotpot, a multi-hop question-answering benchmark that requires reasoning over 2 or more Wikipedia passages. And 2. Fever, a fact verification benchmark where each claim is annotated, supports, refutes, or not enough info, based on if there exists a Wikipedia passage to verify the claim. In this work, we operate in a question-only setup for both tasks, where models only receive the question claim as input without access to support paragraphs, and have to rely on their internal knowledge or retrieve knowledge via interacting with an external environment to support reasoning. Action space. We design a simple Wikipedia web API with 3 types of actions to support interactive information retrieval. 1. Search entity, which returns the first 5 sentences from the corresponding entity wiki page if it exists, or else suggests top 5 similar entities from the Wikipedia search engine. 2. Lookup string, which would return the next sentence in the page containing string, simulating Control-F functionality on the browser. 3. Finish answer, which would finish the current task with answer. We note that this action space mostly can only retrieve a small part of a passage based on exact passage name, which is significantly weaker than state-of-the-art lexical or neural retrievers. The purpose is to simulate how humans would interact with Wikipedia and force models to retrieve via explicit reasoning in language. 3.2 Methods. React prompting for Hotpot QA and Fever. We randomly select 6 and 3 cases 2 from the training set and manually compose React format trajectories to use as few shot exemplars in the prompts. Similar to Figure 1D, each trajectory consists of multiple thought-action observation steps, i.e., dense thought, where free-form thoughts are used for various purposes. Specifically, we use a combination of thoughts that decompose questions: I need to search X, find Y, then find Z, extract information from Wikipedia observations. X was started in 1844, the paragraph does not tell X. Perform common sense, X is not Y, so Z must instead be, or arithmetic reasoning. 1844 and 1989, guide search reformulation, maybe I can look up X instead, and synthesize the final answer, so the answer is X. See Appendix C for more details. Table 1, Palm 540B prompting results on Hotpot QA and Fever. Figure 2, Palm 540B prompting results with respect to number of Code SC samples used. Baselines. We systematically ablate React trajectories to build prompts for multiple baselines with formats as Figure 1, 1A, 1C. A. Standard prompting, standard, which removes all thoughts, actions, observations in React trajectories. B. Chain of thought prompting, cut, which removes actions and observations and serve as a reasoning-only baseline. We also build a self-consistency baseline, CoTSC, Wang et al. 2022a-B, by sampling 21 chain of thought trajectories with decoding temperature 0.7 during inference and adopting the majority answer, which is found to consistently boost performance over CoT. C. Acting-only prompt, ACT, which removes thoughts in React trajectories, loosely resembling how WebGPT interacts with the internet to answer questions, though it operates on a different task and action space and uses imitation and reinforcement learning instead of prompting. Combining internal and external knowledge. As will be detailed in Section 3.3, we observe that the problem-solving process demonstrated by React is more factual and grounded, whereas CoT is more accurate in formulating reasoning structure, but can easily suffer from hallucinated facts or thoughts. We therefore propose to incorporate React and CoTSC and let the model decide when to switch to the other method based on the following heuristics. A. React CoTSC. When React fails to return an answer within given steps, back off to CoTSC. We set 7 and 5 steps for Hotpot QA and Fever respectively, as we find more steps will not improve React performance 3. B. CoTSC React. When the majority answer among NCOTSC samples occurs less than N 2 times, i.e. internal knowledge might not support the task confidently, back off to React. Fine-tuning. Due to the challenge of manually annotating reasoning traces and actions at scale, we consider a bootstrapping approach similar to Seligman et al. 2022. Using 3,000 trajectories with correct answers generated by React, also for other baselines, to fine-tune smaller language models, Palm 62B, to decode trajectories, all thoughts, actions, observations, conditioned on input questions, claims. More details are in Appendix B.1. 3.3 Results and Observations. React outperforms ACT consistently. Table 1 shows Hotpot QA and Fever results using Palm 540B as the base model with different prompting methods. We note that React is better than ACT on both tasks, demonstrating the value of reasoning to guide acting, especially for synthesizing the final answer, as shown in Figure 1, 1CD. Fine-tuning results 3 also confirm the benefit of reasoning traces for more informed acting. Table 2. Types of success and failure modes of React and chain of thought on Hotpot QA, as well as their percentages in randomly selected examples studied by human. React versus COP. On the other hand, React performs chain of thought on Fever, 60.2, 56.3, and slightly lags behind chain of thought on Hotpot QA, 27.4 versus 29.4. Fever claims for supports, refutes, might only differ by a slight amount, see Appendix D.1. So acting to retrieve accurate and up-to-date knowledge is vital. To better understand the behavioral difference between React and chain of thought on Hotpot QA, we randomly sampled 50 trajectories with correct and incorrect answers, judged by EM, from React and chain of thought respectively, thus 200 examples in total, and manually labeled their success and failure modes in Table 2. Some key observations are as follows. A. Hallucination is a serious problem for CoT, resulting in much higher false positive rate than React, 14% versus 6% in success mode, and make up its major failure mode, 56%. In contrast, the problem-solving trajectory of React is more grounded, fact-driven, and trustworthy, thanks to the access of an external knowledge base. B. While interleaving reasoning, action, and observation steps improves React's groundedness and trustworthiness, such a structural constraint also reduces its flexibility in formulating reasoning steps, leading to more reasoning error rate than CoT. We note that there is one frequent error pattern specific to React, in which the model repetitively generates the previous thoughts and actions, and we categorize it as part of reasoning error as the model fails to reason about what the proper next action to take and jump out of the loop for. C. For React, successfully retrieving informative knowledge via search is critical. Non-informative search, which counts for 23% of the error cases, derails the model reasoning and gives it a hard time to recover and reformulate thoughts. This is perhaps an expected trade-off between factuality and flexibility, which motivates our proposed strategies of combining two methods. We provide examples for each success and failure modes in Appendix E1. We also find some Hotpot QA questions may contain outdated answer labels. See Figure 4, for example. React plus CodeSC perform best for prompting LLMs. Also shown in Table 1, the best prompting method on Hotpot QA and Fever are React, CodeSC, and CodeSC React, respectively. Furthermore, Figure 2 shows how different methods perform with respect to the number of CodeSC samples used. While two React plus CodeSC methods are advantageous at one task each, they both significantly and consistently outperform CodeSC across different number of samples, reaching CodeSC performance with 21 samples using merely 3 to 5 samples. These results indicate the value of properly combining model internal knowledge and external knowledge for reasoning tasks. React performs best for fine-tuning tuning. Figure 3 shows the scaling effect of prompting, fine-tuning 4 methods, standard, COT, ACT, React, on Hotpot QA. With Palm 862b, prompting React performs worst among 4 methods due to the difficulty to learn both reasoning and acting from in-context examples. However, when fine-tuned with just 3,000 examples, React becomes the best method among the 4, with Palm 8b fine-tuned React outperforming all Palm 62b prompting methods, and Palm 62b fine-tuned React outperforming all 540b prompting methods. In contrast, fine-tuning. Standard or chain of thought is significantly worse than fine-tuning React or ACT for both Palm 862b, as the former essentially teaches models to memorize potentially hallucinated knowledge facts, and the latter teaches models how to reason and act to access information from Wikipedia, a more generalizable skill for knowledge reasoning. As all prompting methods are still significantly far from domain-specific state-of-the-art approaches, Table 1, we believe fine-tuning with more human-written data might be a better way to unleash the power of React. Figure 3, scaling results for prompting and fine-tuning on Hotpot QA with React hours and baselines. For decision-making tasks, we also test React on 2 language-based interactive decision-making tasks, AlfWorld and Webshop, both of which feature complex environments that require agents to act over long horizons with sparse rewards, warranting the need for reasoning to act and explore effectively. AlfWorld, Figure 1-2, is a synthetic text-based game designed to align with the embodied Alfred benchmark. It includes 6 types of tasks in which an agent needs to achieve a high-level goal, e.g., examine paper under desk lamp, by navigating and interacting with a simulated household via text actions, e.g., go to coffee table 1, take paper 2, use desk lamp 1. A task instance can have more than 50 locations and take an expert policy more than 50 steps to solve, thus challenging an agent to plan and track subgoals, as well as explore systematically, e.g., check all desks one by one for desk lamp. In particular, one challenge built into AlfWorld is the need to determine likely locations for common household items, e.g., desk lamps will likely be on desks, shelves, or dressers, making this environment a good fit for LLMs to exploit their pre-trained common sense knowledge. To prompt React, we randomly annotate 3 trajectories from the training set for each task type, where each trajectory includes sparse thoughts that 1. Decompose the goal, 2. Track subgoal completion, 3. Determine the next subgoal, and 4. Reason via common sense where to find an object and what to do with it. We show prompts used for AlfWorld in Appendix C.4. Following Sridhar et al. 2020b, We evaluate on 134 unseen evaluation games in a task-specific setup. For robustness, we construct 6 prompts for each task type through each permutation of 2 annotated trajectories from the 3 we annotate. ACT prompts are constructed using the same trajectories, but without thoughts. Since task instances are randomly chosen from the training set, it favors neither React nor ACT and provides a fair and controlled comparison to test the importance of sparse thoughts. For baselines, we use Butler, an imitation learning agent trained on 105 expert trajectories for each task type 5. Webshop can React also interact with noisy real-world language environments for practical applications? We investigate Webshop, a recently proposed online shopping website environment with 1.18 million real-world products and 12K human instructions. Unlike ElfWorld, Webshop contains a high variety of structured and unstructured texts, e.g., product titles, descriptions, and options crawled from Amazon, and requires an agent to purchase a product based on a user instruction, e.g., I am looking for a nightstand with drawers. It should have a nickel finish and priced lower than $140. Through web interactions, e.g., search nightstand drawers, choose buttons such as color, modern nickel white, or back to search. This task is evaluated by average score, percentage of desired attributes covered by the chosen product averaged across all episodes, and success rate, percentage of episodes where the chosen product satisfies all requirements on 500 test instructions. We formulate ACT prompts with actions to search, choose product, choose options, and buy, with React prompts additionally reasoning to determine what to explore, when to buy, and what products options are relevant to the instruction. See Table 6 for an example prompt and Table 10 for model predictions in the appendix. Table 3, ElfWorld task-specific success rates sent. Butler and Butler G results are from Table 4 of Sridhar et al., 2020b. All methods use greedy decoding, except that Butler uses beam search. Table 4, score and success rate, SR, on Webshop. IL plus RL taken from Yao et al., 2022. We compare to an imitation learning IL method trained with 1,012 human annotated trajectories and an imitation plus reinforcement learning IL plus RL method additionally trained with 10,587 training instructions. Results: React outperforms ACT on both ElfWorld, Table 3, and Webshop, Table 4. On ElfWorld, the best React trial achieves an average success rate of 71%, significantly outperforming the best ACT 45% and Butler 37% trials. In fact, even the worst React trial, 48%, beats the best trial of both methods. Moreover, the advantage of React over ACT is consistent across 6 controlled trials, with relative performance gain ranging from 33% to 90% and averaging 62%. Qualitatively, we saw that without any thoughts at all, ACT fails to correctly decompose goals into smaller subgoals or loses track of the current state of the environment. Example trajectories comparing React and ACT can be found in Appendix D2.1 and Appendix D.2.2. On Webshop, one-shot ACT prompting already performs on par with IL and IL plus RL methods. With additional sparse reasoning, React achieves significantly better performance with an absolute 10% improvement over the previous best success rate. By checking examples, we find that React is more likely to identify instruction-relevant products and options by reasoning to bridge the gap between noisy observations and actions. For space-saving ottoman bench for living room, the item has options 39 by 18 by 18 inch and blue and seems good to buy. However, existing methods are still far from the performance of expert humans, Table 4, who perform significantly more product explorations and query reformulations that are still challenging for prompting-based methods. On the value of internal reasoning versus external feedback. To our knowledge, React is the first demonstration of combined reasoning and action using an LLM applied to an interactive environment within a closed-loop system. Perhaps the closest prior work is Inner Monologue, IM, from Huang et al., 2022b, in which actions from an embodied agent are motivated by an eponymous inner monologue. However, IM's inner monologue is limited to observations of the environment state and what needs to be completed by the agent for the goal to be satisfied. In contrast, the reasoning traces in React for decision-making is flexible and sparse, allowing diverse reasoning types, see Section 2, to be induced for different tasks. To demonstrate the differences between React and IM, and to highlight the importance of internal reasoning versus simple reactions to external feedback, we ran an ablation experiment using a thought pattern composed of IM-like dense external feedback. As can be seen in Table 3, React substantially outperforms IM-style prompting, React IM, 71 versus 53 overall success rate, with consistent advantages on 5 out of 6 tasks. Qualitatively, we observed that React IM often made mistakes in identifying when subgoals were finished or what the next subgoal should be, due to a lack of high-level goal decomposition. Additionally, many React IM trajectories struggled to determine where an item would likely be within the ELF world environment, due to a lack of common-sense reasoning. Both shortcomings can be addressed in the React paradigm. More details about React IM is in Appendix B.2. An example prompt for React IM can be found in Appendix C.4 and an example trajectory in Appendix D.3. 5 related work language model for reasoning. Perhaps the most well-known work of using LLMs for reasoning is Chain of Thought, COT, which reveals the ability of LLMs to formulate their own thinking procedure for problem solving. Several follow-up works have since been performed, including least to most prompting for solving complicated tasks, zero-shot COT, and reasoning with self-consistency. Recently, systematically studied the formulation and structure of COT, and observed that the presence of symbols, patterns, and texts is crucial to the effectiveness of code. Other work has also been extended to more sophisticated reasoning architecture beyond simple prompting. For example, selection inference divides the reasoning process into 2 steps of selection and inference. STAR bootstraps the reasoning process by fine-tuning the model on correct rationales generated by the model itself. Faithful reasoning decomposes multi-step reasoning into 3 steps, each performed by a dedicated LM respectively. Similar approaches like Scratchpad, which fine-tunes a LM on intermediate computation steps, also demonstrate improvement on multi-step computation problems. In contrast to these methods, React performs more than just isolated fixed reasoning, and integrates model actions and their corresponding observations into a coherent stream of inputs for the model to reason more accurately and tackle tasks beyond reasoning, e.g. interactive decision-making. Language model for decision-making. The strong capability of LLMs has enabled them to perform tasks beyond language generation, and it is becoming more popular to take advantage of LLMs as a policy model for decision-making, especially in interactive environments. WebGPT uses an LM to interact with web browsers, navigate through web pages, and infer answers to complicated questions from LI5. In comparison to React, WebGPT does not explicitly model the thinking and reasoning procedure, instead rely on expensive human feedback for reinforcement learning. In conversation modeling, chatbots like BlenderBot and Sparrow and task-oriented dialogue systems like SimpleTod also train LMs to make decisions about API calls. Unlike React, they do not explicitly consider the reasoning procedure either, and also relies on expensive datasets and human feedback collections for policy learning. In contrast, React learns a policy in a much cheaper way, since the decision-making process only requires language description of the reasoning procedure. LLMs have also been increasingly employed in interactive and embodied environments for planning and decision-making. Perhaps most relevant to React in this respect are Say-Can and Inner Monologue, which use LLMs for robotic action planning and decision-making. In Say-Can, LLMs were prompted to directly predict possible actions a robot can take, which is then re-ranked by an affordance model grounded on the visual environments for final prediction. Inner Monologue made further improvements by adding the eponymous Inner Monologue, which is implemented as injected feedback from the environment. To our knowledge, Inner Monologue is the first work that demonstrates such a closed-loop system, which React builds on. However, we argue that Inner Monologue does not truly comprise of inner thoughts. This is elaborated in Section 4. We also note that leveraging language as semantically rich inputs in the process of interactive decision-making has been shown to be successful under other settings. It is becoming more evident that with the help of LLMs, language as a fundamental cognitive mechanism will play a critical role in interaction and decision-making. What is more, progress in LLMs has also inspired the development of versatile and generalist agents like Reed et al. 2022. 6. Conclusion. We have proposed ReACT, a simple yet effective method for synergizing reasoning and acting in large language models. Through a diverse set of experiments on multi-hop, question answering, fact-checking, and interactive decision-making tasks, we show that ReACT leads to superior performance with interpretable decision traces. Despite the simplicity of our method, complex tasks with large action spaces require more demonstrations to learn well, which unfortunately can easily go beyond the input length limit of in-context learning. We explore the fine-tuning approach on Hotpot QA with initial promising results. But learning from more high-quality human annotations will be the desiderata to further improve the performance. Scaling up ReACT with multitask training and combining it with complementary paradigms like reinforcement learning could result in stronger agents that further unlock the potential of LLMs for more applications. Acknowledgements. We thank the support and feedback of many people from Google Brain Team and Princeton NLP Group. This work was supported in part by the National Science Foundation under grant number 2107048. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation. Reproducibility statement. Our main experiments are done on Palm, which is not an openly accessible model yet. To increase reproducibility, we have included all used prompts in Appendix C, additional experiments using GPT-3 in Appendix A.1, and associated GPT-3 ReACT prompting code at anonymous.foropen.science/r-react2268/. Ethics statement. ReACT prompts large language models to generate more human interpretable, diagnosable, and controllable task-solving trajectories than previous methods. However, hooking up a large language model with an action space to interact with external environments, e.g. the web, physical environments, has potential dangers, e.g. looking up inappropriate or private information or taking harmful actions in an environment. Our experiments minimize such risks by limiting the interactions to specific websites, Wikipedia, or Webshop that are free of private information, without any dangerous actions in the action space design, i.e., models cannot really buy products on Webshop, the research benchmark, or edit Wikipedia. We believe researchers should be aware of such risks before designing more extensive experiments in the future. This concludes the reading of ReACT, Synergizing Reasoning and Acting in Language Models on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.